And finally, ladies and gentlemen, the last way to calculate a change in enthalpy is using the enthalpies of formation. And so this method is actually probably one of the least accurate ones. Gives us kind of a picture, is it endothermic or exothermic? But other than that, it's based upon hypothetical data, so theoretical data, and it can only be used under certain very specific conditions. And those conditions are that it has to be at 25 degrees Celsius and 1 atmosphere. So more often than not, that will be stated in a question, and that's how you would recognize that you're going to use the delta H of formation. And these are symbolized with the delta H. The degree means standard state, so that means it has to be at 25 degrees Celsius, 1 atmosphere, and then a little f stands for formation. So if we think of a molecule like CO2, carbon dioxide, really carbon dioxide is composed of one carbon and two oxygens, and so the enthalpy of formation would be how much energy is either used or released in the formation of CO2 from those three guys. So if the bond energy of CO2 is lower than the bond energies of just those guys by themselves, then it would release energy. If it's higher though, you'd have to put energy in, and so it would be an endothermic version. So if we want to give some values to this, we could take a look at methanol, which is CH3OH, so one carbon, four hydrogens, and one oxygen. So the most simplest elements would be carbon, hydrogen, and oxygen, and if we were to combine those three at these ratios, we would get methanol. So then the standard enthalpy of formation for all of those, we can sum it together and get negative 201 kilojoules per mole. So that means the standard enthalpy of formation for methanol is that value right there. And notice that's the value for 1 mole, not necessarily just one molecule. So it'd be 6.022 times 10 to the 23rd of those right there. And something you got to keep in mind when you do these, you have to make sure that you write your subscripts or your values as they would be under standard conditions, which is 25 degrees Celsius, 1 atmosphere. So like in a combustion reaction, when we generate water, your temptation is usually to write gas because combustion reaction is producing heat, the waters are going to turn into vapor. But for a standard enthalpy equation, since it's at 25 degrees Celsius, which is a little bit lower than room temperature, it won't be a gas, it would end up being a liquid. And what we say is the most basic or most stable form of any element is its standard state, and so that would be 0. So like calcium, silver, sodium, all three solids, they're solids at room temperature, 25 degrees Celsius, 1 atmosphere. They're really the most stable forms, and so their enthalpy of formation is going to be 0. Oxygen, even though this is O2, is the most stable form of oxygen. You won't find oxygen by itself naturally, and you won't find it as O3 naturally. O2 is its most natural form, gaseous at 25 degrees Celsius, so it's 0. And so these are just a couple that you would need to remember then. Most standard form, it's usually 0. And usually, if it's written kind of normal looking and you're not given a value, you can usually assume that it's going to be 0. Especially if it's not a big long molecule or different elements bonded together. So that would give us the enthalpy of formation for a single molecule, but we're not really concerned with molecules, we're more concerned with the entire reaction. So in the reaction you have reactants and products, and it's just as easy as summing together the delta H of the formation, so the enthalpy of formations for the products, and subtracting it from the reactants. Thankfully, the enthalpies of formation are usually given to you. However, you do have them in your textbook, so let's go ahead and mark that page in our textbook. It's actually in the back in the appendix, and so it would actually be appendix number 3, which is called A3, and on the bottom corner you'll see the pages, and it's page A8. So it's appendix number 3, page A8. And there you're going to find an entire list of a whole bunch of different molecules and their enthalpies of formation. Watch out, though, that you watch for states of matter. Sometimes there's multiple states of matter, and they have different enthalpies of formation. So like something that's not normally a solid at 25 degrees Celsius, you have to put more energy into it to make it a liquid, and so that's going to change its enthalpy of formation. And so if you look those up, and I hope you would when you need them, you're going to find out that iron oxide, Fe2O3, is going to be negative 821.4, and then we've written out the other ones as well. So aluminum and iron, both solids, standard state conditions, are going to be 0. Aluminum oxide, though, is negative 167.5.7. And all of those, the units are kilojoules per mole. And remember, delta H is always final minus initial, which means products minus reactants. So it's not just taking those numbers straight down. We're going to do the products and then subtract it from the reactants. And when we sum these together, that little n right there, that means the number of moles. And so like aluminum, there's 2 of them, so it'd be 2 times 0, which winds up being a 0 anyway. But just if there was a 2 right there, or a 3 or a 4, we would multiply that number by that balancing coefficient. And so we are calculating this at standard state, which means we got the little 0 right there. So that means we're talking about 25 degrees Celsius, 1 atmosphere here. And that only applies to those conditions, so this number does. So here we sum together the products, so those two values right there, multiplied the 0 by 2 just for good measure, and then we subtracted it from the sum of the reactants. If we type that all into our calculator, what we're going to find out is that delta H, the enthalpy, in the standard state conditions of this reaction would wind up being negative 854.3 kilojoules per mole. So that means that this reaction is exothermic. It releases negative 854.3 kilojoules per mole for 1 mole of reactants at 25 degrees Celsius, 1 atmosphere. All right, and those are all the methods that we can use to calculate enthalpy. Now, keep in mind, taken one at a time, they might seem pretty simple, but you're going to have to learn how to navigate and figure out which one of the 4 you're going to use. Depends on the data you're given or the conditions that you're set under, which is a big part of AP chemistry, is navigating through kind of the data and figuring out what to do with it. It's one thing to have it all sitting there in front of you, and it's another thing to be told what to do with the data, but to actually use it in the appropriate way is how you show knowledge, and that's really what this class is testing for. So we want to make sure we practice and that we have a good understanding of what's going on.